kind of anticline traps. I'm a kind of structural geologist. I like the traps. I use the traps as a reservoir, okay? I don't like pinch out. Pinch outs for sedimentologists. And you don't see much, very well, the pinch out on seismic. You will see that. Pinch out on seismic is a bloody problem. Because as soon as they disappear laterally, you start to miss them. They still exist, but they are below the resolution of the seismic. We're going to get there. Now, impermeable trap can be shale, can be salt, what you want, or a sandstone with a strongly, basically, secondary replacement of the porosity through a kind of precipitation of any sort of, if it's carbonate, it can be a static precipitation of the porosity. So probably you know better than me the carbonate. Below, you got all the sandstone. All that's below that is a sandstone. And the sandstone which you got on top, the oil that migrated, and below the water, and typically the water boundary between oil and water is a pretty flat boundary. And it's a flat boundary that it goes flat spot. So you see on seismic as a flat spot. So if you see a flat spot, plus the change of polarity, where does the change of polarity come from? In theory, if I do a section like that, the velocity through the depth should change and grow up, because the more I got a compaction due to the lithostatic weight, the more I should expect to have the elastic parameter growing faster and faster than the density. Now what's happened is that in reality, in there, I got an object that got a density and elastic parameter that are more compacted than that one that is rich of fluid of oil and gas. The one rich in oil and gas will have a rho 2 V2 that are going to be smaller than my rho 1 V1. So the amplitude in there, so if this is the positive polarity, in that case the seismic should show me something like that. There's a negative polarity suddenly shading laterally into a regular positive polarity. So these are the trace, and these are the trace. Laterally change of polarity. Now, if I have a sandstone of a sand, or a shale below a sandstone, the only reason I can expect the change of polarity is through, basically, is there a light for that kind of object? After 5 years, you don't understand what is what. Yeah, but that one should somewhere be up, because otherwise you don't see that. Can you close that one?
There's no bulb in there.
No light?
No,
That one managed to.
What's the point?
There's no bulb.
Sometimes they tell kids, they don't have any. They keep it out. They rub it. Sorry. Well, I hope you can see it. But basically what you got is that you got the reflectivity is suddenly changing polarity, and if you follow the reflector laterally, the more you go outside the traps, the more the change of polarity is reaching from a negative to go back to the real positive, in which is respecting basically the compaction of that. We are going to spend times, a kind of couple of hours in 2 or 3 days on that stuff. This is important for you. So we are going to look in detail all the possibilities. But that's an example on where you can have a contrast of impedance that is changing from positive to negative the more you go through that. Okay?
Well, sorry, so if the impedance is negative,
Yeah.
it's all transmitted, but it's change polarity.
Yeah.
Or there's none of it reflected with a change polarity. Is that
Oh yeah, it's reflected but with a change of polarity.
all reflected.
Oh no, but not necessarily. I mean, in that case, it's not all the only way you can have. The all reflection is that to push basically the impedance extremely larger, so that the transmitted component is almost zero.
Right.
But what the theory is telling you is that in reality, the case in which you got all reflected with almost basically no transmission doesn't exist.
Okay.
So you always have a little bit of energy going to the transmission. What you can have is that at a certain point you can have all transmitted, because it goes to 0. So the more that difference it becomes bigger and bigger and bigger and bigger, negatively or positively, the more the transmitted component is always lower. So what you expect to have if you have a bright component that you expect to have between the impermeable and the reservoir with your petroleum inside, okay, much of it is not, I mean, there is not that much transmission across it. Most of that is reflected.
Is that why it's bright? Because it's got more energy?
Yes, that's why it's bright. So, here come, I close the circle. The bigger are the difference between rho 2, V2, rho 1, V1, whatever they are positive or negative, the more is bright the reflection. The more the contrast impedance is important, the more you're going to see it on seismics. Remind you, it doesn't tell you anything about lithology. The only way to understand about lithology is maybe if you got a good well log information, gamma ray, etc., etc. Okay? Everything is clear. We will spend time on that. Don't worry. We will do exercise. Can we stop 5 minutes? Because I see your brain is mocking. It's fine. But by the question you asked me, I'm getting very well. And then we proceed on with the rest of the. Okay. Thank you.